All right, so welcome to Math 383, Complex Analysis. This is lecture, I believe, 28. What I want to do today is talk a little bit about applications of the Fourier transform. You'll basically finish up this topic and then talk a little bit about some just general fun problems. This is the last class before Thanksgiving. So we will be doing Fourier transforms and differential equations. You'll have some homework related to this just so you can see how useful the tools we have been developing are. Anybody know for cultural extra credit who this is and why this person is here? Yes. And what song? Yes, and in that song, they have the key phrase, it's hammer time. And so this is in homage to what we are doing today. If all you have is a hammer, pretty soon every problem looks like a nail. Obviously, it's much better to have a hammer, a screwdriver, a wrench, a crowbar, lots of different things. But for each one of them, you need to know where can I use it? And ideally, you try to apply it in different areas where you might not initially think it could be useful. And again, the people working in those fields have already tried to use their techniques. And they're smart people. If they could have solved it, they probably wouldn't. So if you have a new perspective, you have a real chance of making a contribution. Does not show on your board that someone is trying to join, but it does show on mine. Okay. All right. So we talked a little bit last time about trying to do some applications of the Fourier transform to solve differential equations. Let's talk about that in a little bit more detail. So I said if g of x is the derivative of f and h of x is a multiplication of f by x, then their Fourier transforms are very nicely related. Explicitly, g hat of y is 2 pi I y f hat, and the derivative of f hat is negative 2 pi I h of y. So there's this nice connection between multiplication and differentiation. So let's look at one of them. So consider g of x is f prime of x. So let's compute g hat of y. And now, when you are doing a subject like this, we are eventually going to be looking at differential equations. We will be having to talk about various things. Depending on who you are with, you will speak a little bit differently. Normally, I can argue that maybe you have trouble understanding my accent because I'm wearing a mask. And if it wasn't for that, there'd be no issues with the Boston accent. It's just Boston accent plus now is a little hard to understand, right? So there is an accent that is even worse than a Boston accent or a masked accent. How do some people pronounce the square root of -1? Nope, J. No, of course, a lot of people do pronounce it as I, but engineers pronounce it as J because they are doing problems in electricity where you have I as current, and they do not want to touch that, unlike other things. And so they will use J for the square root of -1. So you just have to be careful when you're looking at things. So a lot of times, if you read engineering books and it talks about Fourier transforms, it will use slightly different language to talk about the same concepts we're doing. If you look at the Laplace transform, or the Mellon transform, or the Fourier transform, they're all related to each other by changes of variables. We saw this with generating functions, moment generating functions, characteristic functions. You just have to be careful going back and forth. I like to use x and y as my variables. Sometimes they use, little f in some textbooks for frequency. So just be very, very careful when you're looking at things, what notation is being used that day. So g hat of y, by definition, is the integral from -infinity to infinity of g of x e to the negative 2 pi I xy dx. But we know what g of x is, right? It's just f prime of x. So it's d by dx of f of x times e to the negative 2 pi I xy dx. What would you like to do now? Interchange what? Say it again. Okay, so how would you interchange the integral and the derivative? Because the derivative is not hitting the entire integrand, it's only hitting part of the integrand. But I'm integrating with respect to, and the x is bundled. So you're close that we do want to do an interchange. Yeah.
And then you pretend you're on.
I wouldn't say use substitution, I would say something else. Of course you could do integration by parts. We're playing as engineers today. That's even more loose than physicists, right? We don't even hiccup as we go over something like this. Yeah, integrate by parts, right? So we want to have u equals dv equals du equals and v equals. Not often in life are things really this clear to you as to what should be what. Any thoughts as to which one should be the derivative term? Right? Really hard to hide it here. It's the f prime of x dx. And so the antiderivative is just going to be f of x. And then u would be e to the negative 2 pi I xy. And then du, we're integrating or differentiating with respect to x. So the derivative, as we take the derivative with respect to x, it will be a negative 2 pi I y e to the negative 2 pi I xy dx. And so it's uv at negative infinity to infinity minus the integral from minus infinity to infinity of v du. So what's going to happen for the uv term? Yeah, why does it go away? Yeah, we want f to decay. We're talking about taking Fourier transforms, so f should at least have some decay properties. Unfortunately, it is possible that f could spike at sets of smaller and smaller measures we march down. So it's not a given that the boundary term will vanish. But if you make some reasonable assumptions about the decay of f, if you restrict to functions f that have some nice decay properties, then there's no problem. And so here we just need to have some decay in our functions so that we go, f has any decay going to infinity. Yes.
So the decay has to be greater.
No, any decay. Because the other term is e to the 2 pi I xy, right. And that's a modulus form. Any decay in f suffices.
So as x goes to negative infinity, doesn't e go up?
No. Because it's e to the negative 2 pi I xy.
Oh, I see.
That's absolute value 1. So this is equal to the negative, and the negative reinforcement becomes a positive, 2 pi I y integral from minus infinity to infinity of f of x e to the negative 2 pi I xy dx if f decays as the absolute value of x goes to infinity. And what's that integral equal to? Yeah, 2 pi I y f hat of y. And here's the first claim, that the Fourier transform of the derivative is a multiplication by that variable times the Fourier transform. And again, the whole point of this is to say, which operations would you rather do? Now, it's nice to be doing this in a complex analysis class, not a differential equations class. We've done contour integrals. So you might say I'm not being fair by saying whose formula we're using, but we have formulas that allow us to do contour integrals and replace calculating these contour integrals with finding the negative first Taylor coefficient. We've converted integration to algebra. This is a huge gain, especially when you consider how unlikely it is for generic integral, for generic function to have a closed form antiderivative. So the fact that we can convert differentiation to multiplication is wonderful. We've already seen we can convert convolutions to multiplications. The Fourier transform of the convolution is the product of the Fourier transforms. Okay, so let's use this to solve a differential equation. Let's say we have the second derivative of y with respect to t minus y of t is equal to negative g of t. I just want to make sure I'm using the same example that's online. Yes, okay. So this is a nice differential equation. Does anybody remember how to solve differential equations like this? So typically what we do is we first say, let's solve the version where instead of minus g of t on the right, we put in 0. Let's find the solutions in that case. Because we know any function y that satisfies y double prime of t minus y of t equals 0 is going, I can then just add that onto this because it's a linear operator. And then we solve the version with g of t. So let's take Fourier transforms. And I'll denote it by using an f like this. So we have the Fourier transform of y double prime of t minus the Fourier transform of y of t is equal to negative Fourier transform of G of t. All right? And so we have to decide what letter do we want to use to represent the Fourier transform variable. We're not going to use y. We're not going to use t. Yes? Yeah, because the Fourier transform is an integral operator. The integral of the sum is the sum of integrals. So let's use maybe omega for the new frequency. Now, on the last page, we just saw that the Fourier transform of a derivative was 2 pi I times the variable Fourier transform. So if we do this twice, we would get negative 4 pi squared omega squared. We get negative 4 pi squared omega squared, and I'll call it maybe y hat of omega, right? Minus y hat of omega equals g hat of omega. Sorry, and this should be negative. Well, this is screaming at you what to do. What should we do on the left-hand side? Yeah, and so we can just solve and we get y hat of omega is equal to, the negatives all cancel. We get g hat of omega over 1 plus 4 pi squared omega squared. So y hat, so let's do the inverse Fourier transform of y hat of omega would be the inverse Fourier transform of g hat of omega over 1 plus 4 pi squared omega squared. So if we can do the inverse Fourier transform, if we can compute that, we've now solved the equation. So the question is, can we find the inverse Fourier transform? So a lot of it comes down to recognizing things. We talked a little bit about the Cdf method when we were looking at probability a while ago. And we saw when we were doing this to calculate the probability of the sum, at one point we had to find the antiderivative of our probability density. And that should scare you. Anytime you have to find a generic antiderivative, you should be terrified because most functions do not have nice closed form. But in the Cdf method, immediately after saying, I now need to use the antiderivative, what happened on the very next line? How did it cancel out? Yeah, we then immediately differentiated it. So it was there for a moment, but we never actually had to do any computation with it. So over here, I have a horrible function that I now have to find the inverse Fourier transform. Can I find a nice way to study this? So we need to understand the inverse Fourier transform of g hat of omega over 1 plus 4 pi squared omega squared. Okay. And this is where the subject gets beautiful. I mean, this is a really nice idea. I will, I'm grabbing this from some notes I found on the web, and I will, happily give credit to them. It's a well-established technique, but it doesn't mean it's not beautiful. So we want to find the inverse Fourier transform of g of omega hat 1 plus 4 pi squared omega squared. This is the same as the inverse Fourier transform of 1 over 1 plus 4 pi squared omega squared times g hat of omega. Okay. When you see g hat of omega, what should you be thinking of? What function is lurking in the background when you hear g hat of omega? I'm sorry? G, right? Is there any value of omega that's really nice to look at this? 0. So imagine instead of having 1 over 1 plus 4 pi squared omega squared, we just had 1 times g hat of omega, and then we applied the Fourier the inverse Fourier transform to g hat of omega. So what is the inverse Fourier transform of the Fourier transform of g? G, right? So you need to prove that you're looking at a space where something like this is true. But the hope is, if I take the Fourier transform and then I take the inverse Fourier transform, I should hopefully come back to where I started. So if I'm looking at a sufficiently good space of functions, this should be good. Unfortunately, I don't just have the inverse Fourier transform of the Fourier transform of g. I have this pesky factor of 1 over 1 plus 4 pi squared omega squared. So I have the Fourier inverse of a function times a Fourier transform of g. Is there much of a difference between the Fourier transform and the inverse Fourier transform? The inverse Fourier transform just uses negative t rather than t. Any results you have for the Fourier transform, an analogous result holds for the inverse Fourier transform. What is a nice result you have about the Fourier transform of something? Yeah, the Fourier transform of a product, the Fourier transform of a convolution is the product of the Fourier transforms. What if I somehow read this as a product of two Fourier transforms? What if there is a function, say, a of x, such that a hat of omega equals 1 over 1 plus 4 pi squared omega squared. Then we have the inverse Fourier transform of a hat of omega, g hat of omega. Oh, but if I have the product of two Fourier transforms, what is the product of two Fourier transforms? It's not the convolution, it's close. It's the Fourier transform of the convolution. So then this would then be the inverse Fourier transform of A convolved with G. Take the Fourier transform of that. Oh, now I'm taking the inverse Fourier transform of the Fourier transform of A star. So this should hopefully then just be A star G, right? So if we can just recognize that 1 over 1 plus 4 pi squared omega squared is the Fourier transform of something, we're done. So you have a couple of ways to do this. One is to try to calculate the inverse Fourier transform of that. The other is to have tables. And so again, I am old enough that when I was learning things, we actually had lots of tables and you had to learn how to use tables. Interestingly, at dinner last night, my daughter was talking about the song Macarena. How many people have been at a song where that has been played and people have danced to it? Okay, you should have really gone like this, but anyway. All right, so my wife and I were talking about when it came out. And I said, I thought it came out when I was in college. And she said, I thought it came out when I was in high school. There is a 2-year difference between us. And so this is one of those few times in our lives where those 2 years have actually mattered. And yes, it was college for me and it was high school for her when the Macarena came out. And so when you have something like this now, we're in great shape. If we happen to have an extensive table of Fourier transform, we then just look at the table and look at, is there anything that transforms to 1 plus 4 pi squared omega squared? And the answer is yes. And so I just brought the notes here so I would have the function. So it is saying that the Fourier transform of this is the exponential function. So let's consider, let's say f of, I'm going to switch back to the variable x because I like the variable x. Let's consider f of x equals e to the negative absolute value of x. Okay. This is a nice function, has good decay, continuous, not differentiable everywhere, but almost everywhere. And we can calculate its Fourier transform. So f hat of y is the integral from minus infinity to infinity of e to the negative absolute value of x, e to the negative 2 pi I xy dx. how should we do this integral? Yes. Okay, how would you split into two? Yeah, I definitely want to split it into two integrals, negative infinity to 0, 0 to infinity. Excellent. In fact, that's the way the notes do it, is they say, let's consider the exponential that's 0 to up to 0 and then decays versus the one that decays and then is 0 beyond 0. So really, we only need to do one of them. So let's say we want to study the integral from 0 to infinity of e to the negative x, e to the negative 2 pi I xy dx. So I will call this maybe the function h of y for half of the integral. How would you evaluate this? We need to do this integral. We have a beautiful technique to allow us to handle integrals like this. We could do a contour integral, yes. How would I do your substitution? Okay, so we could try to just formally argue, but then that fact is going to be, is going to be a complex number. And we have to be a little bit careful. Good. Not imaginary I. Imaginary, is it the wrong letter?
Or y.
Imaginary y, right? Don't do this integral. Let y equal, say, t over 2 pi I. And so we'll have, say, h tilde of t is going to be the integral from 0 to infinity, e to the negative x, e to the negative xt dx, right? For the integral we're looking at initially, this integral makes sense for all real values of y. So as long as t is what? When is this integral going to be okay? We're okay if t is what? So if t is positive, we're clearly okay. Positive real, t is going to be real for this argument. Yes. Okay. So for what values of t? If t is a positive number, we're clearly okay. I need to have an exponential that decays. Well, x is a variable, so I can't say less than x. This is the integral from 0 to infinity of e to the negative 1 plus t x dx. So that should tell you what the critical threshold is for t. What value of t causes me to worry? Not 1. Minus 1. Once t equals negative 1, I have e to the 0. That's clearly not integrable. And then if t is less than negative 1, I'm going to have something that's exponentially growing. So we're okay if t is greater than negative 1. And what we get is that this is just going to be 1 over 1 plus t. But t was just 2 pi I y, so we just get 1 over 1 plus 2 pi I y. And so again, I love using accumulation points to do integrals. Contour integrals and finding a pole and a residue, that's too much for me. I'm getting extremely lazy, this deep into the semester. And by evaluating this when the input is real, everything is well defined. And then in the regions where they agree, everything is good. So this is now the integral from 0 to infinity. You would do something similar from the integral from negative infinity to 0. Then you would put them together, and it would turn out that that would equal the function that we have. So that the function that we were looking at, the 1 over 1 plus 4 pi squared omega squared, is related to the Fourier transform of e to the negative absolute value of x. It would just be y equals a real number divided by 2 pi I. So why is this a pure imaginary? Because for all those values, they're equal. Right? We just showed if we take y to be a pure imaginary number, then this integral makes sense as long as t is greater than -1. So take your sequence to be, all numbers of the form t over 2 pi I, where t is greater than -1. And so you have infinite, you have a continuum, not just accumulates, it's not just a discrete set, it's a continuum. If you want, take t goes from 0 to 1. For that whole interval, they agree. If you want to take t to be 1 over n, for all those values, they agree. Okay, any questions about this? So I will give you the link so that if you want to look at the rest here, you can. There is a link on this page where, as they go through the discussion, they talk about the double-sided complex exponential, which is either the negative absolute value of x. This is the Laplace distribution, or up to your normalization constant. They go through this calculation in great detail. But this should hopefully show you the power of what's going on. Yes?
Sorry. Once you get the convolution in the past class, then how do you get from the convolution? The convolution is an integral. How do you then get to your g?
Well, we have the inverse Fourier transform of the Fourier transform of A convolved with G.
Right.
So the inverse Fourier transform followed by the Fourier transform followed by the inverse Fourier transform should just get us back to A convolved with G.
Right. But we don't want A convolved, we want G.
No.
No,
I mean we're trying to solve this equation. We have y hat of omega is this expression on the right-hand side.
Right.
So if I take the inverse Fourier transform of both sides, I then get y of t is going to just be my function on the right. It's just going to be A star G. That's going to just be the answer. It now solves the problem. So at this point, we're now done. Now, one thing you might be a little bit concerned about is we have missed some solutions in this. So if you actually go through and do all the details, and they do a wonderful job about this, it talks about the fact that we are restricting what space of functions we look at. So if we look at the initial question, so the initial question was y double prime of t minus y of t equals negative g of t. You normally start by looking at y double prime of t minus y of t equals 0. And so this is very similar to the difference equation for the Fibonacci numbers or something like that. We could try guessing, y of t equals e to the at. And when we take the derivative, we get y prime of t is a e to the at, y double prime of t is a squared e to the at. And so we would get a squared e to the at minus e to the at equals 0. Therefore, what does a equal? Plus or minus 1. So the solutions to, let's call this equation 1, we'll call this equation 2, to equation 2, C1 e to the t plus C2 e to the negative t. And one of the problems is when we try to actually solve it using the Fourier transform, this is going to be missed, I believe. Why might this be missed? Yeah, no decay. So if we're trying to solve these things, there is a danger of missing things and just being careful of what space are you looking at. This is an introduction to the topic. This is not a full class in differential equations. This is not a full class in using Fourier transforms to solve it. I'm trying to just give you enough of a sense that this is a good connection, that problems like this can be solved. There's links in the article about, just like a short page or two about how you would solve like a heat equation or something like that by taking Fourier transforms and inverting them. But what's the inverse Fourier transform or the Fourier transform? It's a contour integral. You're integrating along just one side. So then you use techniques from complex analysis to complete the contour. Or you do some kind of accumulation point argument saying, well, I can evaluate for these special values of the parameters, in which case I can then extrapolate everyone else. So a big part of this is where do functions live? And we're going to talk more about that later. But since this is the last class before Thanksgiving, I wanted to just do two. And one of them is inspired by, or actually almost identical to, a problem I got my freshman year in physics at Yale from great professor, Professor Burke, who wanted to make sure we had something to talk about over the Thanksgiving table. And I hope you have more success than I do in finding people around the table to talk about that. So the first problem is here, if you're drunk, is a unit circle, okay? And I have some number of points on it at some locations. And I claim, and again, maybe, that there's always one point such that the product of distances from Z star, let's XY to X1, Y1, dot, 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 Xn, Yn is at least 1. These are arbitrary points. No matter what points you give me, I can do this. Can you prove that you can make the product of the distances as small as you want? Yeah, how would you do that? Yeah, basically just run the point into one of your points. So clearly we can make the product as small as we want. The claim is that no matter what points I give you, you can always find a point where the product of the distances is at least 1. So let's go by induction. Is it hard to do if there's one point? Can you find a place to put the point on a circle of radius 1 such that the product of the distances is at least 1? Yes. So what do you have to stay away from? The point. So in fact, if I draw two segments of length 1, these are actually going to be equilateral triangles. And then anything in here is okay. Has to be at least 1. If it's more than 1, you should be able to adjust a little bit because we know it's 0 at some point. So by continuity, if it's greater than 1, you can make it 1. So if there's one point, there's no problem. What if there's 2 points? What's the worst case to you? I mean, without loss unit, 1 point is here. What's the worst case for you if there are 2 points? Yeah, opposite sides. And so if you can then show that if I just choose a point over here, maybe for my XY, I want that to work. Well, again, this is 1, this is 1. So this is 60 degrees, 60 degrees, 60 degrees. I'm okay. We all agree that with 2 points, there's definitely a region where I'm going to be safe. What about 3 points? What's the worst configuration with 3 points? Yeah, maybe roots of unity. And then if some of the points are closer, then that would mean something else is further apart. But it's starting to get more involved to prove that this is actually the worst configuration, right? And now what you would have is you would have this point over here. And if you look at what's going on here, oh, it's just going to perfectly make it. So that's 60 degrees, 1, 1, 1, 1, 1, 1. So if that truly is the worst configuration, you're okay. But as we start getting more and more points, it's going to get worse and worse and worse, right? And this is even assuming that you can show that this is the worst configuration. Any thoughts on how we might want to try to do this? We could, of course, continue by induction, or there might be a better way. Yes.
I was wondering if you could look at like the linearity expectation.
Okay.
So with just one point on the circle, if you go down the second point randomly, what's the average? What average is the log of the average?
I'm worried as soon as you say expected values, because that's a probabilistic argument. And what you could be trying to say is that there will always be, say, a positive measure of places to choose from. There is an argument you can make for other problems like that. Think about it. Think about whether or not you can make that work. I'm worried about having that work here. I did slip originally, might have been on purpose. And before I wrote XY, I wrote something else. Anybody notice what I wrote? I wrote Z star. So let's call these maybe Z1, Z2, Z3, Zn. Instead of calling the point Z star, let's call it maybe Z. Where do you want to put the point Z? I'm sorry? All right, so let's put it at, so let's construct a function f of Z is going to be the product of Z minus Zk. K goes from 1 to n. And again, I'm not going to square or take absolute values. But if I took the absolute value of this, this would be the distance between Z, the product of the distances, right? What do we know about f of 0? What does f of 0 equal? 1. Or at least an absolute value, right? So can someone finish the proof now? I have a function f. Yeah, not constant, attains maximum boundary. This is a really nice application of complex analysis. This is not a problem about complex analysis. So I would love to see a non-complex proof of this. But we know the maximum. And so by the maximum modulus principle, it has to attain its maximum on the boundary. Since it takes on the value 1 at the origin, it has to be at least 1 on the boundary. Absolutely love this backdoor function. Right. So the last is from Professor Firk. I heard about it at Yale in Physics 460, 1992. So define integral on a function f by the integral of f is the integral t goes from 0 to x of f of t dt. Solve integral of f equals f of x minus 1. I want to try to find a function such that when I apply this integral operator to it, I get back my function minus 1. Anybody have any guesses of what function might work? Is it going to be a polynomial? Good, we know it's not a polynomial. Do you think it's going to be a trig function? Doesn't seem like it's going to be a trig function. What other functions do we know? We don't know many functions. Exponential. So let's try exponential. So guess f of t equals e to the t. We then get the integral of f is the integral from 0 to x of e to the t dt. That's e to the x minus e to the 0. That's f of x minus 1. So you solved it. Now let's prove it. Trigger warning. We're about to proceed as physicists. If playing fast and loose with mathematics bothers you, you are welcome to leave now and have a happy day. All right, so again, we have defined integral of f to be the integral t goes from 0 to x of f of t dt. So we want to solve integral of f equals f minus 1. So that's the same f minus the integral of f equals 1. Everybody agree with it? Just moving things over. This is the same as 1 minus integral acting on f equals 1. We did this earlier today. We just factored things out. So this is the same as f equals 1 minus integral inverse acting on 1. Right? I'm just applying the inverse operator. What's 1 minus integral inverse? What does that equal? I'm sorry? Yes, exactly. It's just a geometric series. Geometric series where r equals integral. So f is 1 plus integral plus integral integral plus integral 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 plus dot 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 acting on 1. So 1 acting on 1 gives me 1. Now I have integral acts on 1. What is the integral of 1? Well, let's do things over here. Integral, oh, it's supposed to be in red. You know, it should be like a warning color or a color to enjoy. The integral of 1 is the integral t goes from 0 to x of 1 dt, which is just x. Now the integral of 1 is the integral of 1. So that's the integral t goes from 0 to x. The integral of 1 is just the function x. I now use my variable t, so it's just the function t dt. What does that equal? You could say t squared over 2, but, well, yeah, absolutely, yeah. First of all, it's x squared, not t squared. X squared over 2 factorial. And then integral of 1 is the integral of the integral of 1, which is the integral t goes from 0 to x of t squared over 2 factorial dt, which is x cubed over 3 factorial. And so as we now put this in, we get 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 dot. This is physics at its best, right? You're playing fast and loose with the math, but at the end of the day, getting the right answer. So the question becomes, why did this work? Well, there must be a way to justify these steps. Depending on what space of functions you're looking at, we have an operator. What does it mean to take the inverse of an operator? When can you use the geometric series formula to invert an operator? For what space of functions is this valid? That is not under realm for discussion for today. This is just to give you a beautiful example of what can happen if you're a little fast and loose with the math. I think my favorite moment of his class was, he said, the following step will take you 6 weeks to justify in your math classes. Moving on, we see, and this is something you really want to get into the habit of being able to do. When do you need to understand every single line, every single detail? When can you stop and say, I'm going to just use this. I'm going to treat this as a black box, use this result and move on. But being aware of what are the dangers, what are the possible pitfalls. We have to make sure that we can define this operator 1 minus integral inverse. When can we use the series expansion? All right, have a good Thanksgiving all, and we will resume on Monday afterwards.